Example 87. Human heights are normally distributed. Assume the average height for women is 63.6 inches with a standard deviation of 2.5 inches. Then find the height that separates the bottom 90% of all women from the top 10%. All right, what makes this problem interesting or different is that they don't say find the probability. They say find the height, right? So we're not looking for a probability, and that is a dead giveaway that even though the problem says normally distributed, we're not doing the type of problem that we did earlier. The type of problem we did earlier always asked us to find the probability, right? Here we're asked to find a value, so a height, a score, a weight, whatever, something other than a probability. Whenever that happens, you know you're working with a problem that's using the normal table in reverse. This means we're trying to find a value that corresponds to a certain percentile or a certain probability. So what we're going to do here is actually do everything backwards. We're going to draw the bell curve still, though, because it does say normally distributed. So let's start out with a very familiar set of steps, and that is to, of course, create a bell curve, and then label the axes like we've done in the past. So the center of the z-axis is 0. The center of the x-axis will be the average. It says the average height for women is 63.6 inches, or about 5'4". The standard deviation, they say, is 2.5, so we're going to put that number in. And now if we're looking for the height, right, that separates the bottom 90% of all women, here's where things become different. We're actually going to be looking for a value on the curve. So before we do this problem, what I want you to do is get in the habit of drawing two little mini curves here. So draw two little tiny mini bell curves. And the reason why we're doing this is to answer a simple question at the outset. And that simple question that we want to answer is this: where should I put a slice in the curve? These problems are always going to involve at least one slice in the curve, and we have to figure out where that slice goes. So in other words, am I dealing with a slice on the left, or am I dealing with a slice that's on the right? We're trying to find the location of this slice, and we want to figure out which drawing I should be using. So here's the question. If you looked here, would this location on this bell curve correspond to the score that, or the height that separates the bottom 90% from the top 10? For example, where is the top 10 on the curve? Is it down here, or is the top 10 here? Well, I would say the top 10 is here, right? It only makes sense to me that the top 10 would be at the top of the curve, and then the bottom 90% would be below that, right? Think about this. Could you have 90% below this point? That's impossible, because below this middle line, we only have 50%. So clearly, this is the only drawing that makes sense. Because of that, I'm going to basically eliminate this as my option, and I'm going to say, aha, it must be this drawing then. So that means I need to put a slice on the right-hand side of the curve, not on the left. All right, once you've determined that, which may seem like a trivial point, but it's actually one of the most important steps of the process. Once we've determined that, we're going to think about what we know about this slice. We know that above it is 10% because it separates the top 10%, right? So we know that this value is 0.1000, or 10%. We know that's the case because it tells us that this cut in the curve separates the top 10% from the bottom 90. Now think about it. If this little chunk is 10%, then what's the amount from here to here? Well, remember, half of the curve is 50, right? So this would only make sense if this was 40%, right? Which is the same as 0.4000. So 10% in this part, right, leads to a decimal value of 0.1000, and 40% here leads to a decimal value of 0.4000. Together they make the 50% that is the half of the curve. Notice I'm not shading anything because we're not looking for an area. We actually know the areas, don't we? I know this is 50, I know this is 40, and I know this is 10. I don't need to find an area, and that's not what this problem is asking about. What it wants to know is this: what is the height that corresponds to this location on the curve? This is our question mark. It is that we're trying to figure out, right? And so that's a very important thing. Now, from there, I know the following logic must be true. In the past, I used to take this approach. I used to be given an x value, and from an x value, I went over to a z-score, right? And then from a z-score, I would move over to an area, right? Or a probability. And let's think about how I did that. From the x value to the z value, I used to do that transition by using a formula, right? The formula was the z-score formula. And then when I went from z-score to area, I used a table. Do you remember the z-table? That's how we got the area from the z-score. So basically the path was from the x value to the z-score to the area. Now we're going to be going backwards. We're going to go area to z-score, and from z-score to the x value. So this is why I call this the normal table in reverse, because we're going backwards. We're starting with a known area. And why am I circling this area and not this one? Because the table that we work with, which is going to be the vehicle to go backwards, just like it was the vehicle to go forward, that area is related to the table, right? Not this area. Our table gives us the the value from this line to the center. Remember that? It always works from the line you look up to the center. So the z-score that goes here corresponds to the 40%, not the 10%. In other words, the table associates this location with the area from the line to the center. So it's actually the 40% that's associated with this z-score. Now, once I use the table backwards in order to find the z-score, then I will then use my z-score plugged into my formula, and I will find x. Now, the formula is the z-score formula still. However, we're going to do a little algebra on the formula, and we're going to produce the following alternative formula. It's the same formula, just solved for x instead of solving it for z. And it's going to be this formula, z sigma plus the mean. If you do a little algebra on your z-score formula, you will be able to produce this by just solving for x, right? And once you have this formula, you will then plug in the z-score that we found, plug in the standard deviation, which we already know, and plug in the mean again, which we already know, and that will produce the x value that we're interested in. And that is how we will ultimately find the answer we're looking for. So again, we're going to look up this area because this area is associated with this z-score. Once we find that z-score, we're going to plug that z-score into this formula below, and that will produce our x value. So everything is backwards from what we did before. Remember, for every z-score on the z-chart, we have an associated area, and that area is from the line to the center. And likewise, for every area from the line to the center, we have an associated z-score. So you could use either one of these to find the other. If you know the z-score, you can find the area. If you know the area, you can backpedal to find the z-score. Let's go demonstrate how that's done. That's the next part of what we have to do. Let's look up 0.400 in the body of the z-table in order to produce this missing z-score. Okay, so we're trying to look up the area 0.4000, or 40%. And remember, we start in that first column here and try to find the closest thing to the number we're looking for, right? The closest area in that first column to the number we're looking for. So it looks like we go from 0.38 here to 0.40. So maybe it's in this 0.38 row here. Let's go across. So the 0.12 row actually. Go across until we see something nearby. Well, it looks like to me that these two numbers are pretty close, right? This last one is 0.4015, that's 15 10,000ths away. And this one's 0.3997, only 3 10,000ths away. So I think that's the right number we're looking for, the closest thing to 40%. And that's in the 1.28 position. So 1.28 is the value we need. Okay, so it looks like 1.28 is the closest z-score to the one we're looking for. So 1.28 is the z-score we find from the table. One little heads up here, it should be positive because it is to the right of 0. We want to make sure that we check the sign because remember, the table never gives us a negative. If we're on this side, we need to make sure to make this value negative. Since we're on the right-hand side, we can leave it positive. From there, we're going to take that z-score and plug it into this formula with our other given information, and that will finish the problem for us. So ultimately, the height that we're looking for, the x value we need is going to be the z-score 1.28 times the standard deviation of 2.5 plus the mean, which is 63.6. All right, we plug all that in. Let's see what it comes up with as our answer. So we will have 1.28 times 2.5 plus 63.6. And when we're done, we get 66.8. This is about 5'7" because 60 inches, of course, is 5 foot. So 6.8, the remaining amount, is in inches, so it's about 5'7". So that's the height that a woman has to be taller than 90% of the female population. If she stands at 66.8 inches, she will be taller than 90% or only shorter than 10%. And that's it. That's the answer to the question.